Hello, welcome to our presentation on scaling attributed network embedding to massive graphs. It's a great honor that we have received the Best Paper Award from this conference. I've been teaching data science for 5 years, so the most basic form of data science looks like this. You have a big table. In this example, we are in the financial market setting. So each row corresponds to one stock, and each column corresponds to one attribute of this stock. So there's also one attribute that we are trying to predict. So this is called the target attribute. The basic form of data science we have discussed in the previous slide focuses on one single entity only. As database researchers, we know that the database contains not just entities, but also relationships. The entities and relationships jointly form a data graph. In general, graph data analytics is more powerful than data analytics on a single table. In this example, Tesla is connected to CEO Elon Musk, and Elon Musk is one of the co-founders of PayPal. The success of PayPal flows from itself to Elon Musk and then to Tesla. So now we can see that although the market share of Tesla is very small at the moment, we expect it to grow very rapidly, just like PayPal. This information is not available among the original attributes of Tesla. On the other hand, graph data analytics is also difficult to do. On the left-hand side, I have single table data analytics. So here I have standard tools such as scikit-learn. As a result, the difficulty of doing so is pretty low, and you can give this task to a student intern. For graph data analytics, the standard way is to build a graph neural network. As a result, the difficulty of doing so is very high, and you need a senior AI fellow to perform this task. In this paper, we present Practical Attributed Network Embedding, or PANE. The idea of PANE is that you transform a very difficult problem, which analyzes the attributed graph, to a simple one, which is to analyze data in a single table. This transformation works by condensing information about this particular node, which includes edges and nodes and attributes around this node, to a fixed length embedding vector. So how is the performance of our proposed method PANE? In terms of effectiveness, we have compared our method PANE against several state-of-the-art methods, which mostly use neural networks. And we found that we are better in almost all the settings on all the datasets. In terms of efficiency, in our experiments, we have very big datasets. For example, this one has 59 million nodes, almost a billion edges, and 2,000 attributes. We have computed the embedding of all the nodes in this graph. It took us around 12 hours to finish everything. So far, we have focused on one particular application of PANE, which is attribute inference. There are two other important applications of PANE, which are link prediction and node classification. Our method PANE is built mostly using database technologies with a little bit of machine learning flavor. So there are three main technologies in PANE. The first is that we measure node to attribute affinity via random walks. The second is that we compute those embeddings, which are the final results, through a procedure called joint matrix factorization. And third, we make full use of multi-core parallel computation capabilities in modern computers. First, let's take a look at the random walks in the proposed method PANE. There are two types of random walks. The first type is to move forward. So this goes from a node to an attribute. The second type goes from an attribute backward to a node. In the forward walk, you start from this node U, and at each step, you stop with a certain probability alpha. And then finally, you stop at this particular node V, and after that, you pick an attribute of V randomly. With forward random walks, we can define this concept called node to attribute affinity as follows. FUR is defined as the normalized probability that the forward random walk from this node U ends up sampling attribute R after you finish the random walk. Similarly, we can define backward random walk and also this corresponding concept called attribute to node affinity. So what you do is that you start with this attribute R, and then you randomly pick a node S, and now you start the random walk from S, and finally you end at another node V. So the attribute to node affinity is defined as the normalized random walk probability from this attribute R to the final node V. Next, let's look at the second main technology in PANE, which is the computation of the embedding vectors. These are the main outputs of our proposed algorithm. In our proposed method, we built three embedding matrices: X forward, X backward, and Y. X forward and X backward are for the nodes, while Y is for the attribute. In order to compute the three matrices, X forward, X backward, and Y, we formulate the problem as an optimization program. There are two objectives here. The first one is X forward into Y should be roughly equal to F, which is the node to attribute affinity matrix. The second one is that Y into X backwards should be roughly equal to B, which captures attribute to node affinity information. To solve this optimization program, we perform a joint factorization of forward and backward matrices to obtain the three embedding vectors. So in this process, we formulate the joint factorization as a least square optimization problem, and we solve it through gradient descent. And we furthermore, as an optimization, we use randomized singular value decomposition to obtain a very good initial solution to the problem. As a result, we only need very few iterations to converge to a good solution. So in our experiments, we found that the number of iterations is as low as 5, and the results have high quality. Here is how the optimization problem is solved. On the left-hand side, you see how the system is initialized. First, we decompose this matrix F with singular value decomposition. So this gives you U and V and sigma in the middle. So now with this decomposition, we can compute X forward, which is U into sigma, and also Y, which is assigned to V. Note that Y here is unitary, which means Y transpose times Y is equal to an identity matrix. Therefore, we can derive X backward, which is equal to X backward times Y transpose, and this equals B. And this part is Y, which we carry to here. So X backward can be computed by backward matrix B into this Y, which is initialized to V. On the right-hand side, here is how we do the iterations. So we follow a general strategy of coordinate descent, which means you fix one thing and you update the other, and then you fix the other thing and update the first thing. So here we have two things to update. One is X forward and Y, the other is X backward and Y. So each of the update is performed using a method called stochastic gradient descent. So these are very common strategies used in machine learning. Finally, PANE is fully parallelized on multi-core computers. So we don't have time to explain the details here. If you're interested, please read section 4 of our paper. Next, let's look at our experimental results. So our experiments involve 8 different benchmark datasets. In addition, you can see that Google Plus has a very special property that it has a lot of distinct labels, which we are going to predict, and it has a large number of attributes per node. In our experiments, we compare against 10 competitors, which are taken from the state of the art at the time we wrote the paper. So here are the results. As you see, this red line with a square, this is us. So now you see in all those diagrams, we are always at the top. In summary, we have built a method called PANE, which transforms a very difficult problem, that is to analyze a large attributed graph, to a simple one, which is to analyze a single table. PANE contains mostly database system technologies. In addition, we also have a machine learning flavor, which is to solve the joint matrix factorization problem. I hope you enjoyed this paper. Thank you.